down the center of the bowl, we have that basic parabolic shape. It's a little easier to envision or visualize if you think about if you slice this bowl down the middle, you could see that basic quadratic shape right there. Same thing with this bowl, just a little bit smaller version, but it still has that same basic parabolic shape. So think about that. If you sliced it, you could clearly see that parabolic shape. So what we're going to do today is we're going to take some measurements, and we're going to look at those data points and see that if we plot those points, we do in fact get that basic parabola curve. So we're going to start with some water in our big bowl. And what I'm going to do is I'm going to measure the height of the water from the center of the bowl to the surface, the top of the surface of the water. Measure that with my daughter's pink ruler here, and I get that is right at 1 inch. Okay, and the next measurement I'm going to take is measure the diameter across the surface of the water, from one side of the circle to the other, down this right through the center. If you think about the water in the bowl, the top of the surface is going to form a circle, and we're finding the diameter of that circle. Okay. So if we measure that, again with our little handy-dandy pink ruler, that comes out right at 8 inches. Okay, and what we're actually going to be plotting is the radius versus the height. So if we have a diameter of 8 inches, that means we have a radius of 4 inches. Remember, radius is half the diameter across the circle. Okay, so we have our first set of points. We need to get a second set. We're going to add water to our bowl and measure that height once again. Again, from the center to the top of the surface of the water. And that height this time is 1.5 inches. Okay, and then again, the diameter across the top. This time I'm right at 8.5 inches. 8.5 inches for a diameter will be 4.25 inches for the radius. See what I'm doing here is I'm forming ordered pairs that I'm going to plot. Radius versus height. Okay, we're going to take 2 more measurements just so we have a nice selection of points. So I'm going to add more water to my bowl. Measure the height again. Okay, so what I have here are 4 sets of data points. Radius versus height. I'm going to plot those points. Okay, so 4, 1, 1, 2, 3, 4 on the X. Gives me a point approximately right there. 4.25 is just over the 4, and I'm going to go up to 1.5 this time. So we're here. And then at 4.5, I'm at 2.25, so I'll bump up just a little bit. And then 4.75, I'm going to be still not all the way over at 5. 4.75, I'm going to go up to 2.5. Okay, so do you see how these points are gradually going up, so they're forming something that looks very similar to that? Well, if we finish this graph out, you can see it's really flat here, and that's because the bottom of the bowl flattens out. But if you could imagine what the symmetrical left side would look like, it would basically be that basic parabolic shape that we were talking about. That when we graph a quadratic equation, that's the shape that we're going to get. Okay, so let's take a real quick look at basic quadratic equation, y equals ax squared. What I'm going to do is I'm going to show you that if you plug these points into that equation, we're basically going to get something real close to this same A value every time. A could be anything for any quadratic equation. We're gonna find that these points give us basically the same value each time, and what that's going to show me is that these points do in fact model a quadratic equation, okay, or something very close. It's not going to be perfect because again, these were real quick measurements, and these bowls, you know, do kind of have a flat bottom, so they're not absolutely perfect parabolas, but they're really close. Okay, so let's do a little math here, and what we're doing is we're going to plug each of these ordered pairs in for x and y. This is my x value, this is my y value. Okay, so if I take 4 and plug it in, 4 squared, let's just write the points right down here, y equals ax squared. Okay, so I have 1 equals a times 4 squared. Okay, so I take my handy calculator. I know that 4 squared is 16, so I have 1 equals a times 16. Well, I want to know basically what a equals. I want to know if each time I'm getting something real close to the same answer for a for each of these ordered pairs. So the way I would solve this equation is I would divide both sides by 16. And what I get when I divide 1 by 16, just to change that to a decimal, you're going to get 0.0625, which is, if we round that off, because we know this is not going to be perfect here, but when we round it off, we're going to get 0.1. Okay, now the next set of ordered pairs, same concept, plugging this in for y, this in for x. So 1.5 equals a times 4.25 squared. Okay, and if I do that math, 4.25, and then 1.5 divided by that answer gives me that a equals 0.08, which again would round to a equals 0.1, just like I got here, okay, when we do our rounding. Okay, and if we do the last 2 points, we're going to get something very similar to that. 20.25, 2.25, my second answer. Okay, this time we get a equals 0.11. So still, we're at approximately a equals 0.1. So we can see if we do the last point, you're going to get basically the same thing, something real close. It's going to round off to 0.1. So that shows me that these points do in fact very closely, they're not perfect, but they do all round off to the same value for a. So that tells me that these points do in fact very closely resemble that parabolic nature of a quadratic equation. And just real quick, I want to show you just a couple more things. Again, we talked about this bowl is a different size, but it still has that same basic shape. And just while I was talking, I was noticing my tea kettle here, same basic parabolic shape. If you look around your world, outside, inside, you're going to find that quadratics are all around us. So math is everywhere, and you should just be on the lookout for it. And look for quadratics whenever you can, and you'll be surprised where you might